Shouting at you from West Virginia. Or somewhere, anyways. Alright, but I do have Joke of the Day, and I know that you are ready and waiting for Joke of the Day because it is the best part of the day. So let's do this. What can you serve but never eat? A volleyball! And now we're going to serve up some combining like nth roots. Now remember, we talked before about being able to combine up like square roots. Same thing's going to happen here. And so remember that when we combined up these like radicals, we said as long as the radicals were the same, that made them like terms, and we could work the coefficients and retain what's making them alike. Remember I said that when things sit up against each other, that indicates multiplication, and multiplication is expressed through the word of. So when these two are sitting beside each other, they're being multiplied, and so that would indicate 9 of these square roots of 3. 9 of these square roots of 3. Same thing happening here. Sitting up against is going to indicate multiplication. So we have 8 of these square roots of 3. So now what we're going to do is we're going to say if we have 9 of these square roots of 3 and we're adding in 8 more of these 8 square roots of 3, how many of these square roots of 3 do we have? Well, we said that meant we had 17 of these square roots of 3, and it's going to sit beside each other indicating multiplication. So like I said, what that tells us is as long as the radicals are the same, we're going to retain what's making them alike, the radical, and we're going to work those coefficients. The same thing can happen with nth roots. You can add and subtract those nth roots as long as they are alike. Similar concept. For them to be alike, they have to have the same indices, and then the number underneath has got to be the same. So as you look at this, and this actually should be a 3. I miswrote that. There we go. So the indices have to be the same, and the numbers underneath the indices, or in other words, the radicands have to be the same. So these are not quite the same, but I can certainly do a little bit of simplification to make them the same. Because I know that with that 81, this cube root is going to indicate I'm looking for a number that I can multiply by itself 3 times to get an 81. Well, 3 times 3 is 9. 9 times 3 is 27. Not quite big enough. 4 times 4 is 16. 16 times 4 is 64. Not quite big enough. 5 times 5 is 25, and 25 times 5 is 125. That's too big. So I cannot think of a number that I can multiply by itself to create an 81. So what I'm going to do is break it down, break it down, break it down. Going back to the 80s, we're going to break it down. So that 81 then, I'm going to call it a 9 times 9. And remember, in terms of simplifying these radicals, I'm going to look for a perfect triple or a set of 3. When I see a perfect triple, then that means I'm going to take the cube root of that triple, or in other words, a perfect cube, I'm going to take the cube root of that cube. Or when I see a set of 3, the set of 3 makes a perfect cube. And so if I see a set of 3, I'll take one out and it'll dissolve the others. Now I don't see a set of 3 here, and let me go ahead and copy this down. Now there's nothing that I can do with this cube root of 3. I cannot think of a number that I can multiply by itself 3 times to create that 3 underneath. And that 3, I can't break it down, break it down, break it down into anything useful, because 3 is just 3 times 1. That doesn't help at all. So this is as simple as it's going to get, but let's take a look at this one. That 9 is 3 times 3. So what I have there is 3 times 3 on the first 9, and then 3 times 3 on the back 9. Now I feel like I'm playing some golf. So notice what we have here is I've got a triple. And remember, when I have a triple, I'm going to take one out, and it's going to dissolve the other 2. And I'm looking for a triple because this index of 3. So now what I have, and let me get this out of here, I'll just rewrite it here in a minute. So now what I have, remember when I take this 3 out, how do I combine it with this one? This is a great big huge multiplication problem. Now that's subtraction, yes. But right here is multiplication, right here is multiplication. So when I take this 3 out and combine it with that 3, I'm going to combine it by multiplying. So what I'll have is 3 times 3, here's the cube root, and this 3 is the only thing that's left there. But the nice thing is, now out here I've got 9 cube root of 3 minus 4 cube root of 3, and notice that the radicals are the same. Cube root of 3, cube root of 3. So it's like I've got 9 of them, minus 4 of them. Well, if I have 9 of them, I take out 4 of them. How many of them are left? 5 of them. So I have 5 of these cube roots of 3. And that is how I'm going to combine those. So now let's take a look at the other example. Let me put it back up there. Okay, so here's that second example. And remember, in order for them to be like radicals, we have to have the same indices. Fourth root, they are the same index. But notice that what's underneath those radicals is not the same at all. So I need to do some simplification in order to make them like radicals. So I'm going to take a look at this 48. I'm looking for a number that I can multiply by itself 4 times to create a 48. Can't think of that number because I know that 4 times 4 times 4 is 64, and I know that 3 times 3 times 3 is going to be a 27. So it's between those two. So I'm going to simplify that 48, and again I'm going to break it down, break it down, break it down. And so that 48 then is going to be, first thing I can think of is 6 times 8. Now you may have thought of something else like 16 times 3, but that's perfectly fine. We're just going to keep breaking it down, breaking it down, breaking it down until we see a set of 4 or a perfect quad. Now, this x, nothing I can do with this, but notice this y to the 4th. What would I multiply by itself to create a y to the 4th? Yeah, a y. So I can take that 4th root of this and go ahead and take it out. When I do, I have y and then 4th root of 6 times 8 times x. Now, I'll just go ahead and finish this one out and then we'll grab this one. That's 6 times 8. Can you think of a number you can multiply by itself 4 times to create a 6? Nope. How about 4 times to create an 8? Nope. So I'm going to continue to break it down, break it down, break it down. So that 6 is going to be 2 times 3. The 8 is going to be 4 times 2. And once again, I'm looking for a set of 4 because I can't think of anything I can multiply by itself 4 times to create a 2, or 4 times to create a 3, or 4 times to create a 4. So I'm going to continue to just keep breaking it down, breaking it down, breaking it down. So that 4 is going to be, oh, sorry, that should be a 3. This 4 is going to be a 2 times 2. Here's the other 2. And there's the x. And notice, aha, I do have a set of 4 sitting right there. So remember what that means is I'm going to take 1 out, dissolve the other 3, so that outside I'm going to have a 2y, and underneath I'm going to have a 3x. Now I need to work with this one and break it down because I can't think of a number I can multiply by itself 4 times to create a 768. That's a little big for me. So what I'm going to do then is I'm going to break up that 768, and if you cannot think of something that will go into 768, at least it is even. If it's even, it's certainly divisible by 2. So I'm going to do 2 times, and this will be a 384. I cannot think of a number I can multiply by itself 4 times to be a 384, so let's break that one down as well. And again, if you can't think of what will go into 384, the fact that it is even means it's certainly divisible by 2. So 2 times 192 will give me a 384. Can't think of a number I can multiply by itself 4 times to create a 192, so I'm just going to keep going with this. I'm going to keep breaking it down, breaking it down, breaking it down until I see a set of 4. Now, 192, once again, it's even. I'm going to divide it by 2. So 192 divided by 2 will be a 96. And I can't think of a number I can multiply by itself 4 times to create a 96. So I'm going to go with this. I'm going to say, you know what? I got 3 sets of 2 right here. I'm going to go ahead and divide this by 2. So there I have a set of 4. And 96 divided by 2 is going to be a 48. Don't forget the x that's in there. So now here is my set of 4. I'm going to take 1 out and dissolve the other 3. 1, 2, 3. They're gone. So that now outside I'm going to have a 2y, and I have 4th root of 48x. Now, be careful because some people get really excited. They go, wait, 2y, 4th root, 2y, 4th root. They're like terms. But remember, it's not the coefficient that I'm worried about here. It's the radical that I'm worried about. 4th root of 3x, this is 4th root of 48. I am not done with this one. So I'm going to keep working with it. And I'm going to break up that 48. It's 6 times 8. And keep this one, I don't want to lose it. I can't think of a number I can multiply by itself 4 times to create a 6, nor 4 times to create an 8. So I'm going to break that up a little further. 6 is going to be 2 times 3. 8 is going to be 4 times 2. And still can't think of a number I can multiply by itself 4 times to create those. So what I'm going to do is I'm going to continue breaking it down. And I will take this 4 and I will turn it into a 2 times 2. So here's the 2, here's the 3, here's the 4. And aha! There we go. I have a set of 4 right here. And so I'm going to take one out, I'm going to dissolve the other 3, and that will leave me with, here I'm going to write down that first term, and that will leave me with, take the 2 out and multiply it here. 2 times 2 will give me 4, and I'll be left with a 3 and an x underneath. And now, oh my goodness, we've got like radicals. 4 through to 3x, 4 through to 3x. So this says I have 2y of them minus 4y of them. And remember, once I've got like radicals, I'm going to retain what's making them alike. The radical is what's making them alike. So I'm going to keep that. I'm going to keep that 4th root of 3x. And I'm going to work those coefficients. 2y minus 4y is a negative 2y. And ta-da, ta-da, there it is. I know, that's a lot of work there, and some of it could be sped up if you knew some of these roots and if you could split your numbers up a little bit differently, but this is the premise behind it. Just like with those square roots, you can only combine them, in other words, add or subtract them, if the radicals are the same. Same thing here, the radicals have to be the same, and that means indices have to be the same and the radicands have to be the same. Once you get them the same, just work those coefficients. I hope that helps. Have a great day.